A very good afternoon or good morning, depending on where you are. We are only 80 participants on the webinar, so I'm asking kindly that we wait a little bit and we see that the numbers push up, and then we get started. Thank you. Hi, Thomas. I don't know if Salma has something to say before we start.
Frozen. Dr. Dong is frozen. Or is it only on my screen? I'm going to put the objective as Dr. Helen, can you hear me? Can you hear me?
Yes, I can.
Oh, okay. That's fine. So, good afternoon once again. Thank you very much for joining in. Thank you so much for making it up to the day 5, our final day of this webinar series. We want to thank you for your commitment and your patience and your willingness to learn and understand everything happening in here. We just hope that our hope, as usual, is that you are up to date so far with what has been covered in the last 4 days. By going back on the YouTube channel and trying to catch up so that you are not completely behind and so that you'll be able to make use of these sessions. So please do not forget to fill in the registration form. Link will be shared in the chat by my colleague here, and we wish you all the best on the final day. Thank you very much. Thank you very much, Dr. Helen. It looks like Dr. Dong has a problem with the network, but I'm sure he will get it sorted. Thank you. Over to you.
Okay, thank you so much. I think we can get started, and then as other people join in, they'll get us on the way. Let me share my screen. So like I highlighted yesterday, today we're going to look at generalized linear models. All right, but basically there are only 3 parts that we're going to see. We're going to look at contingency tables and chi-square and how is chi-square used. Then later we'll look at logistic regression, and then the final part will be the Poisson regression, hoping that the time will allow. Okay, let's dive into the first part, contingency tables and chi-square. But let's just remind ourselves a little bit, because when we talk about contingency tables, then it implies that things to do with categorical data are going to set in. We know that statistics about analyzing facts, okay? After getting the facts, organizing and then collecting data, you have to come up with a what? With a conclusion of your audience. So there is this particular type of data that is collected. So we have different variables, which are the column names, the roll cost, the type, height, design, speed, and then the duration. Under each variable, so these variables we have, when you look at them very closely, we have what we call the value of the variables, especially if they are quantitative in nature. Quant implying that you can measure them, all right? And then in case you pick only one entry, for example, if you pick the first row, then it implies that that is an individual variable that you've picked out with the respective with other sets of data in terms of type, height, design, speed, and then duration. And we know that most of the time that these variables are in form of an attribute that keep on changing different values. For example, we have variable type, which is grouped as either wood or steel, or design, which is the different levels that we have. We have the sit down, the inverted, etc. All right, but the rest are the speed and the duration. They are quantitative in nature, as we will see. As I've already explained, the categorical variables, as we're going to see them in more details. And I believe by now we clearly know what categorical variables are, because at the end of the day, we see that within the categorical variables, these are variables which have got different levels. All right, like I've already talked about within the type is a categorical variable with different labels. They can either be in wordings or you can label them each into values. And then with a quantitative one, these are numerical in nature, and most of the time they can be measured. Still using the similar example, we can see that on the slide. Okay. Still more to that, there is we have here some data that was collected about primary and secondary school students using surveys. Of course, this was just a random sample about 40 US high school students. And one of the questions that were asked that which would you prefer to be? That was the question. So the variable is preference, okay? And then among the things that we are supposed to select, we had rich, happy, famous, healthy. All right. So as they were doing a survey, they moved out there. So as a student, they had to select any of these categories. So the preference status is a categorical variable. But of course, within this survey, there were many other variables that we can see down here. And then it's up to you to, given the data, it's up to you. You should be in position to be able to say that we are looking at the data set that is displayed at hand. Maybe this variable is categorical, or this other variable, it's what? It's quantitative. Sometimes categorical variables are referred to them as qualitative in nature, but the categorical word or variable is one that's really so much common in our ears, so I'll keep to that. So I'm not going to go into asking you that, okay, basing on what you're seeing, which is categorical or which is quantitative. I just have a feeling that we can be in position to tell that Right now, this is categorical, this is qualitative, because from Monday up to today, we are talking about the same language. So, referring back to the same question of the preferential status, all right? In this particular, what we are seeing on this slide is that when they were asked, we saw there are 4 of them. So when they were asked, what we are seeing that there are some that chose for them, they prefer to be famous. Others chose to be happy, healthy, or rich. And when you look at the frequency table, most of the time it helps us to show us a quick distribution on how the different variables are, especially when it comes to summary statistics. All right. So what we are seeing within the frequency table, we are seeing that most of the students, their preference was to be happy, followed by those that wanted to be rich, famous, and then the last one wanted to be healthy. Of course, they had their own reasons as to why they went ahead to pick up those different categories. With the relative frequency, it's about computing the frequency into percentages, and it's usually each cell divided by the what? By the total number. So that is the frequency that we can look at. Another example, when we're displaying categorical data, I don't know if some of you know about the story of the Titanic, whereby within that data set, it's a common data set that many people tend to use when they're demonstrating how to analyze data. We had a variable class whereby people chose. We had some members that were in the first, so the levels we had first class, second, third, and then the crew itself. And then we have the count, so call them the frequencies. Still, we see that the variable class is categorical as it has 4 different levels, the respective frequencies or the counts, and then from there, we can move on and get the percentages. Also, apart from showing the summary statistics, as we are seeing, getting to know the frequencies, then their percentages, we can also display categorical data in different ways, especially in visualization. Still, this has been done since Monday, but just to touch up that with categorical variables, you can still go in for a bar or for a bar chart, for a bar graph. As we saw the number of people on Titanic, we have those who belong to the first, the second, third, and then the crew. We know that usually words speak more loud, diagrams or pictures speak more louder than words. And depending on the audience that you're considering, many people like to see these numbers displayed as graphs because they can easily attach meaning or get familiar with what you're explaining. So we can use bar graphs in case we want to do a categorical for one variable. You can as well go in for the pie chart. I mean, at the end of the day, the way you're going to explain your results is going to be the same. It's not going to change. And the meaning or the conclusion that you're going to have is going to be the same. Here, we can also, with this particular variable, you can also have, you can display a bar chart side by side. In case of 2 categorical, we have 2 categorical variables whereby we had some that we had the age groups and then the type of phone that we expect that this particular group of ages should have. We see the iPhone, and with the different bars are attached to the different ages. Then the Android, and then we have the others with respective of the age range between 18 to 34, 35 to 54, and then 55 plus. Okay. So that was just something brief about how our data should look like, especially when it comes to categorical data. And we know that when we have categorical data, then we can also represent it in different ways. For example, the contingency table. If you don't want to use the word contingency table, the other common word being used is the cross tabulation. And usually contingency tables, they summarize categorical data in rows times columns. So you can have maybe a 2 by 2, 2 by 2 type of contingency table, 2 by 3. You can have as multiple columns or rows as you want. And we usually see the combination of frequencies of two categorical variables, okay, now that we know what these variables are. So here, in this particular example, we are having two variables, gender, whereby somebody can be a male or a female. And then we also have smoking, which is either somebody smokes or somebody doesn't smoke. So with this particular example, we are creating a 2 by 2 contingency table, all right? Where we are having that the number of males that smoke are 30, those that don't smoke, the count is 10. And then the females, the yes is 20, and then the no is 40. So this is just an example of representing two categorical variables in a cross tabulation or a contingency table. Remember what we said with the contingency table, it just gives us a summary of two categorical variables represented in form of rows and then columns. We are going to still move on into R and see, well, in case you have data, how can you do that? I'd created what we expect, okay, how to create a contingency table in R. But in case still we go into the R script, we are going to see this particular thing again, and then I'll explain it into more details. But briefly, if I'm to mention here, when we go to R, I created just a matrix over 2 by 2, okay? In this particular case, you know, with a matrix, you can be able to come up with a contingency table. And then I said, I used the matrix command, all right? And then inside the matrix command, I said concatenate, bring these values together. I'm just picking the table that I have here. So now I'm trying to say, how can I put it in R, all right? So I say, then I have 30, 10, 20, and then 40. I say the number of rows are true, and then by row, the number of rows are 2, and then by row it is also true. So as we move on, I created an object data whereby I sealed my matrix. That's where I want my matrix to be. I can be in position to go ahead and get what data is within R. I'm going to show you that. And then I also went ahead to have the column names of my data as yes or no. That is the smoking, if with the columns. Then the rows is gender, where I have the males and then the females. So using the command as data, I was able to print out how my data looks like. This time around, when we run it in R, we'll see that we are having the column names and then the row names being attached, and then we shall display our table, the object name in this particular case, which will give us the contingency table. Okay, I'll talk about the last bit as we move on. All right. So here, still with categorical data and the chi-square test for independency. As we said that with categorical data, we can go ahead and with the two variables and create a contingency table. But just creating a contingency table might not be enough, okay? We might need to dig further to understand, we want to know whether the given variables are independent or not. And so in this particular case, the chi-square tends to come in. So one thing we want to test that are these two categorical variables independent? Remember, with the chi-square test, we test for independency. That is our null hypothesis that the two variables are independent. as the null hypothesis. And then the alternative that no, they are not independent. The variables are what? The variables are associated. So we are going to discuss and then see within R, and you're like, okay, how given the null hypothesis and the alternative, can we come up with a conclusion to say that, well, these variables are independent or they are not independent, as the test says. Okay, with the chi-square statistics, test statistics, we're going to see all the things within R, and then we attach much more meaning. We know that when we come to chi-square statistics, what is very important for us to understand is that it measures how much the observed frequencies. Remember, with the observed frequencies, these are just the counts that you see from your data, all right? The observed frequencies in your contingency table divert from the expected frequencies. When we talk about expected frequencies, these are the ones that you expect if the variables were independent. Please note that, because at the end of the day, when we talk about a chi-square, it is built on the divergence between the observed and then the expected, everything squared divided by the expected. All right, so this is the chi-square test statistics. So when we look at that particular measure, and we are saying that with the expected count, the number you would expect in each cell of the contingency table, if there is no relationship between these variables, okay, assuming that in the previous example that we had gender and then smoking. All right. So, but what we are seeing in there, we are seeing observed values or observed counts. And we want to know what should be the expected values in case the two variables were not associated or were independent. Okay. Among the different assumptions of the chi-square that we need to put at the back of our mind, we talked about the data being categorical, and then we assume that these observations are independent. But also, it is recommended that the expected frequencies, as we see how we are going to compute them, they should be greater than 5. Most of the time, if you run a chi-square, whereby some of the cells are less than 5, it is likely to give you a warning, especially in R. And then the moment such a scenario happens, the best alternative would be that you use the Fisher exact test. So, because for it caters for small number of what? Small number of frequencies. And still, when you look at this particular code, it's still the same thing about the contingency table. So, I want to, before I move on to option 2, I want to add in a new slide, and then we explain more about the expected count or the expected frequency, such that when we go to R, everyone is following very well. Okay. All right. Like I mentioned, when we talk about expected frequencies, okay, remember the main theme about the chi-square, whereby I say that it measures the difference between the observed frequency, what you see in your data, how it diverts from the expected frequency, the expected frequencies. And here we are saying that what you should expect in case these two variables are what? Are independent. And we know that if you want to calculate the expected frequencies, we do it for each cell, okay? I'm going to just give just a very simple example. Assuming that I've got males and then I have females. This is, I'm just going to give us a simple demonstration. And then the drink choice, here I've got like tea, and then here I have coffee. All right. If this is coffee, all right. And then I also have the totals at this particular end. I'm going to just keep talking, but try to follow the expressions. So I want to create a 2 by 2. All right. If from my data I observe that the males are 8, then the females, the frequency that take T are 12, then this is a hypothetical example. So if I have 3 there, 7, then I have 3 here. So the totals in this case, how do I get the totals? I just sum the rows. I have 15 there, I have 15 here, and then also the totals that I'm going to have here, I'm going to have 20, and then here I'll have 10, and the grand total, which is referred as the grand total, is always what? It is 30 in this particular case. So this is my contingency table, and it has got observed frequencies, or you can call them observed counts or values. All right. And we said that for us to come up with the expected frequency, okay, the value that you would expect if the variables, if the 2 variables are independent. Most of the time, the mathematical formula or the general formula we usually have the row totals. Okay, I'm going to denote it as that, and then we multiply by the column totals. You can also put subscripts in case you want, and then everything out of the what? Out of the grand totals. This side gives me the row totals, and then here I've got the column totals. So, but remember, we are supposed to get the expected frequency for each cell. So in case I'm to compute the expected frequency for cell, if I call it E11, okay? If I call it E11, I'm considering the first row, first column. It implies that the row total is 15 and then the column total is 20. So when I come here, it's going to be 15. We multiply by 20. And then we divide everything by what? We divide everything by 20. No, the grand total is 30. And we end up, if you compute quickly, we end up with 10. So what we are seeing here is that, so we would expect 10 males, okay? We would expect 10 males to choose T if gender and drink choice were independent. That is the reason behind. But in this case, actually, the observed is what? The observed is 8. So, and the difference between the observed and the expected is what the chi-square is built on. So, and then of course you can get other cells using the same approach. You can compute for male coffee, female tea, female coffee. So in short, what am I trying to say? That when we talk about observed counts, we are looking at what you really saw in your data. But with the expected frequency, it's what you should see if there is no association between variables. In this particular case, there is no association between gender and the drink choice. So now, given that we've grasped what the main key concepts are here, then I'm going to continue. Okay. Before we move to R, let me also talk about the other option that you might take, because after calculating the chi-square, we talked about the chi-square test statistics. Then within the chi-square statistics, it has got different degrees of freedom. So, and now that we know the different hypotheses, with the first one, no independency, implying that, no, the first one, there is independency. Then the second one, they are dependent. So sometimes you can also, apart from considering that, you can consider if you don't want to, we can also use the p-values if you want to come up with a conclusion to check if either we reject the null hypothesis or we don't reject the null hypothesis. And there are also some other cases whereby people use chi-square tables. And what usually the rule of thumb here is when the calculated is greater than the tabulated value, or you can call it the critical value, then we reject the null hypothesis. With this particular example, it is still talking about the same thing. This one was about like, okay, in case you use tabulated, if in case you use a chi-square frequency, a chi-square table, all right, we still have two variables. We have the area, which has three levels, and then we have the theft. Okay, either they steal, you have the burglary, the robbery, and then the car theft. So we still have two variables. Which two variables? We are seeing the observed frequencies. We can go, this is a 3 by 3. We can go ahead and compute the expected frequency. It doesn't matter how many rows or columns that you have, but after calculating the expected frequency, then we can go ahead and compute the chi-square test. So that is what this part is all about. Okay, I'm not going to go into details given that I've explained how we go about it. But what conclusion are we having? When the test statistics, the chi-square test statistics was calculated, we are seeing that and the calculated value is 23.13. So remember, it is a 3 by 3. We can, from this test, we can be able to come up with the degrees of freedom with the formula R minus row minus 1, total number of rows minus 1, total number of columns minus 1. Since they're all threes, so we have, we'll end up with 4 degrees of freedom. If we are taking our null hypothesis to be set at a level of significance of 0.05, basing on whatever statistical table that you've used. In the first place, if they use a 1% significant level, if we to consider this, what we are seeing is that the critical value is 9.488. This value is less than the calculated value, implying that the calculated value, the 23.13, is greater than the tabulated value. And so in that case, we are going to reject H naught of independency, and we said that they are dependent. They went further as well to consider it at apart from 1%, then there was also considered at, I think at 5%, yes. And then still the same results came up that the calculated was still greater than the tabulated. And so in that case, we still reject the H naught and accept the alternative that there is dependency, implying there is an association between the two variables. I'm going to stop here, and then now we move on to R. Like I mentioned, if you check in yesterday's folder, all these slides are there. So you can pick them and then follow through as I'm moving. So I'm going to stop sharing, unless if there is a question, then I go to R and we see how can we operate that when using R. When you check in the Google material folder, we are using the contingency table chi-square.r script is what we are using. Okay, so let's go through together. You can open at your end, and then we can move on the same page. I'm going to explain still briefly what we just talked about, and then we can interact, and you can give me a conclusion based on what we are saying. What do you think? What is happening? So let me check in that. Let me ask in the chat. Are we on the same page? Can you type 1? Okay. In case you have a question, please type it in the Q&A, and then we can start from there. Okay. Can we open our script, the contingency tables underscore chi-square.r now? Let's open our script, and then you can still use the script that you've downloaded, or you can create a personal one just for you to practice and get to know what we are doing. I'm going to first use a very simple example on what I've just elaborated, and then later we shall use a data set, and then see what about in case I've got a data set, how do I do it? Still the same story can happen, and then we check the conclusions. Okay, so still, if you come to, I'm using this particular script, people, the other facilitators have been talking about R, and I believe at least right now we are somewhere when it comes to now how the R workspace looks like, right? So I want here, when you come to I want to create a contingency table. Like I was explaining earlier in the slide, I created a matrix of a 2 by 2. Okay, I'm considering the example I have within the slides, whereby I'm considering 2 categorical variables. One is gender, and then the other one is smoking. With gender, we have males and females. And then with smoking, either somebody smokes, that is the yes, or one doesn't smoke. So, and I'm using a command matrix. That's where I put everything, because we know when we talk about matrices, what should come at the back of your mind is that we are considering row by column. So I want to create a 2 by 2 matrix of my data that I have. But I want to put everything inside what I've called the object data. It's just a name that I've chosen. If you want to change it, there's no problem. You can give it something else. Remember what we said, this is just an assignment operator. You can say less or dash, or you can say it is equal to. So if I run line 30, line 3, if I run that line, what I'm seeing is that I don't see the output immediately. Yeah. So if I want to see how my data looks like, so I go now on line number 4 and I run the object. Okay, when I run line number 4, when you check in my console, if you look in my console, I'm having now 30, 10, 20, then 40. Okay, this is the data I'm trying to bring in now. But I'm like, this is not enough. Yes, that is my data. But now I want to attach the column names and then the row names. Remember, with the column names, it is smoking. So I'm like, I'm going to use a command, call names. In bracket, I want to create the call names for my data. That is the matrix I created. So I assign it to be equal to C, then I put 2 options, the yes or no. I go to the call names, I do the same, and I assign male or female as my gender. So if I run line number 5, okay, I run line number 6. So now for me to see that it has been effected, I use the command as table data. So I want to see now, how does my table in this particular case look like? So when I run that particular line, if I want to see now the table itself, then this is what I'm getting. So I've got the yes, no, and then the male and the what and the female. I've created a contingency table of a 2x2. All right, with gender and then smoking. Remember, we can as well go ahead and add margins. All right, what I was calling the total rows, and then the total columns using the add margin, using the add margins command. This is my command. And then inside, where do I want to add the margins to? It's on the table object. So I run line, when I run line 9, what do I see? I see the total sum of rows 40, 60, and then the total sum of columns of 50, and then 50, and the grand total as 100. Sometimes also, like we said, you can explore more. You can maybe only add you can say add margin, and you specifically want to only add the columns, or you can specify that you want to do it for the rows only. But in this particular case, we want both. All right, now that I've seen how to create a cross tabulation or a contingency table of my data, maybe you have your data somewhere and you want to do some simple analysis. So I want now to go ahead and test for independency between gender and smoking. And how do I do that? We are saying that, okay, let's use the chi-square test, because what we are considering are two categorical variables. So I run line 9. When I run line 9, I named my object chi. Okay, so I want, and the command for running a chi-square test, it is chi-sq.test. It is this command here. Okay, remember we talked about the help command. In case you're running something and you're not so sure of the command, you can use the help to give you more details. But with the chi-square test, this is the command we use. And then if I want to see the results, I'm going to run the object chi. So if I run my object, this is the results that I get. Okay, it's a Pearson chi-square test with Yeti's continuity correction. So I'm having the chi-square, the x squared as 15.042. What I can say about the chi-square value. Remember we said that when we're talking about chi-square, the statistics looks at the divergency between the observed and the expected. So most of the time, when our x squared, a large x squared value, it implies that there is a greater difference between the observed and the expected frequencies or counts. And so this one gives us a strong evidence that that's a strong evidence against the null hypothesis of independency. But if we find a scenario where the x squared is small, it implies that the observed frequencies are very close to the expected values. And so in this particular case, it gives us little or no evidence against the null hypothesis. All right? And what we are saying with the degrees of freedom, we are having only one. Remember, it's a 2x2. So if we are using our formulae, we end up with 2 minus 1, 2 minus 1. We end up with only 1 degree of freedom. And the p-value is 0.0001052. All right? With a degree of freedom, it tells us how many pieces of information are free to vary once you know the totals. So in this particular case, if we have one degree of freedom, it implies that we only have one piece of information, that is, we are free to vary if we know the totals. That is the total columns and then the total rows. Now let's move on to the p-value. We are seeing that the p-value is less than the null, which we said to be true at 0.05. That is the level of significance. And so in this particular case, we can conclude that the two variables, gender and smoking, are dependent. So we reject the null and then opt for the dependency between the two variables. All right. Also, maybe in case you are interested to compute the expected values, I mean, like we've been saying, R can do everything that you want. So when you come to line 13, remember my chi object, that's where the chi-square, that is where I perform the chi-square. So I can as well come and say chi within my chi-square. Then I'm like, get for me the expected values. So this is chi $expected. With the expected values, we said that these are the values that you would expect if there is no relationship between these two variables. So if I do that, of course, it's just going to give me, it's going to just give me, yes, still it's a contingency table, but it gives me the expected values for each what? For each cell. So that is for the simple part, okay? Like I've just created a matrix and then I'm like, okay, let me briefly go through and see how to compute a chi-square. And then from there, I'm able to come up with a conclusion that, well, if I test for independency based on these two variables with my p-value less than 0.05, I have I have a strong evidence to say that to reject the null hypothesis of independency and conclude that the two are dependent. Okay, I'm going to pause again and ask in the chat if we are still together before we move on to how about in case you've got a data set, okay? Maybe you have your data and you want to run some associations, okay? To see because remember when you're running your analysis, most of the time you start with the descriptive to get familiar with your data, running the frequency tables, running the summary statistics for continuous variables, and then we go on to checking if there are association between these two variables, okay? Or are there association with the if you have explanatory variables and the response variables. All right, and then later you can move on to the multivariate analysis of considering the kind of model that you want to use on your data set. Okay. Somebody's having if chi is denoted by a small, what does it imply? When you check in R, okay, how chi is being written, it is a C. Remember somebody one time within the differentiation that we've been having said that R is case sensitive. So when you're writing out the chi-square test, it is small. They are all small, small. They are in small case. Let me say like that. They are in small case, and our test is this one. All right. When you use a capital, R is going to complain to tell you that maybe there is an error or whatever test that you've put doesn't have it. So you have to put that into mind. Okay. Somebody said error, object expected not found, object chi not found. When you look at when you follow closely, I don't know if you've been able to reach at line 9. After line 9, if you can, after line 9, what you can do before even you create, Kai was just an object. So it shouldn't confuse you. You can even give it a different name. You can just put Kai, you can write chi-square test. Okay, chi, CHISQ, then dot test. All right. And then inside, we are going to put our table. All right. So, and then you can run that. We can run line 10. Of course, when you run line 10, it will still give you similar result. Why I wanted to create another object, all right? Okay, maybe if Kai is confusing you, if I put hi as my object and I remove, but now I want to make hi, all right, to be equivalent to put everything. Hi is my object to be within line number 10, everything to be equal. That Chi as an object is equivalent to my chi-square test. All right. Why I created an object is like I wanted the information inside the chi-square table to create for me the expected frequencies. All right, so if I run that and then I run high again, I'll still have that. Then all I need to come here, if I'm to edit, and then I run that, it will give me the same as that. Of course, like we said, sometimes you just need to play around with the data. All right. What about, let's try that on line 10, I just I just put a $sign and then I write expected. What will it give me? When I run that, I still come up with similar results. So when you play around with the different commands, remember the point is understanding what each does. And as time, since it's something that you have to practice as you move on, then some of these things will become part of you. I hope I've helped that one who was saying that he has a problem. What do you do if the expected value is less than 5? I mentioned that in that particular case, if it is less than 5, R, most of the time, when you're running using R software, it will give you a warning. And the best alternative would be that you use the feature exact test to be able, and in that case, what you'll be looking at, since you want to see if there is an association, you need to check for the p-value, all right, if it is less than 0.05 or greater than. But still, when you're presenting your results, for example, maybe you're writing out your table, you have to indicate somewhere below the table that basing on this variable, I ran the association using the Fisher exact test. So that is the other option that you can do. All right. I think we can continue. How do we clean data? Stephen is asking, how do we clean data? You find that data cleaning is really a big deal, all right? But there are some things that you have to put into consideration. Okay, I'm just going to talk about it roughly. There are certain things to do with data manipulation. I don't know if you heard about data manipulation. With the data manipulation techniques, you are able to clean your data, but it still goes back on what are your objectives? You've set your objectives properly. You've collected your data. Sometimes you may need to delete some columns or to delete some entries. I'm just speaking in a more of a simpler way. You might need to delete some columns or rows, or you've got incomplete entries, and you find that if you delete them, they might not affect your result depending on the number of entries, or you can have other methods on how you can be able, like, okay, if you've got many missing values, you need to ask yourself, what computations approaches do I need, okay, to fill in these missing entries? Do I need to use the impute such that those cells are being filled? Sometimes maybe you might need to change the names of the variables that you have, and all these ones, they have different commands that you can use. So I would encourage you to understand the objective very well and then get to know what are the different data manipulative techniques that I can use to clean my data. Okay. All right. There is also a colleague who is complaining about the employee. I think you're far ahead of us, so let's move on the same page. Okay, let me ask a question. Now, can we continue? Can we go ahead? Type 1. Great. Um, Egata is asking that I should repeat the interpretation of the chi-square obtained. Our chi-square is 15.042. I mentioned that what we need to, when you're having x squared, all right, okay, chi-square squared, when you look at that particular value, there are two things that you need to put at the back of your mind, because we said that sometimes you might compute a chi-square when it is, remember, it depends on it still goes back on the number of entries that you have and also the degrees of freedom that you are considering. But literally, what is trying to tell us, remember, chi-square is built on the difference between the observed and the expected frequencies, or call them counts, call them values, like the way that I explained earlier. But what we can grasp here is that I said that for a larger x squared value, what does that imply? It implies that there is a greater difference between the observed and the expected counts, or you can call them values. And so in that particular case, it gives us a strong evidence. It gives us a strong evidence against the null hypothesis of independency. All right. In other words, it gives us at the back of our mind the instinct that should come that we are able we should be able in position to reject the null. All right. But in case it is very small, I think when you're running analysis, you've come across such a scenario. If it is very small, it implies that the observed data is close, very close to the expected value. And so in this particular case, we have little or no evidence of rejecting the null hypothesis, or no evidence against the null hypothesis of independency. Okay, so let's continue now. I'm going to leave that at that. Now, what about in case we collect our data? We want to use our data. The other one's just a simple example, but the conclusions are going to be the same. I believe that you've got the employee data set still in the folder. That's what we are going to use. When you check in that folder, let me first stop sharing. When you check in the folder we shared in the materials, the employee dataset should look like this. Please check. We have different variables. We have We have gender, which is categorical, M or F. We have years in school, years spent in school, all right? We have job category, which is also categorical. We have current salary. We have a beginning salary. We have time on job in months. We have a previous experience. It is also, all these ones are, we can see they are numerical variables. And then we have the minority. Minority is categorical. Either one belongs to 0 or 1. The zeros are the minority, then the ones are not the minority. This was data that was still collected on in the US from different graduates. And they are looking at if there is an association between different variables, if they are related to somebody's salary. Okay, that's why they put the current and then the beginning. So they wanted to see, how do the other variables influence somebody's salary? Does one belonging to a minority category influence your salary? What about your previous experience? What about the time you spent on job? How about the type of job that you do, all the years that you spent in school? That's what this data set is all about. Okay, let's go back to R. All right, remember to set the working directory as it has been demonstrated. It is still the same thing. There is nothing that we are changing. So if I run my directorate, okay, remember my employee.csv, it's within this folder, that is the training R on my end. So I believe it should be different from your side. And then I'm going to assign an object name employee. That is the name of the data set I'm choosing. And then I assign it with the read.csv. Remember, we talked about importing data. You can use read.csv when you're calling data being saved with a CSV. Or if you don't want that, you can have a data set, which still I shared, employee saved as an Excel sheet, whatever that you want. And then when I run that, I'm able to call my data set employee. So when you look in the environment, what we are seeing is that we are having 470 observations of 9 variables. So let me check in the chat if we've all reached line 20. We've managed to run line 21 successfully. Okay. Okay. I think this is great. I'm seeing many ones, so I'm going to continue. I hope we're on the same page now. No one is stuck behind. Okay, great. So I've already mentioned about the different variables, okay? But you can still use the call names command to see. So these are the variable names that we have. But remember when we're demonstrating the nature of the data set, you need to first understand the structure of the data set, all right? And the command was str. Then I want to see the structure of the data set of employee. I'm just putting in these commands, but I mean, you can also do it at your end because we've been seeing them since Monday. So when you come here, just something I wanted to highlight is that the ID that is just identification for each employee. So like they can say this one has identification 1, 2, 3, and so on. What we are having that gender is a character, so we need to convert that to a factor. Years in school, yes, it's an int. Then job category, we have different job categories. So we also need to convert that to categorical. And then we saw salary, yeah, they are quantitative, int, they're just numerical. But what we need to change as well a non-minority category. And we mentioned that if for you want to convert characters to factors, you can use as a factor or you can use factor, all right? And I think line 26 to 28 are okay to everyone. Converting characters to categorical variables. You want to show R that, my friend, look at these variables as categorical ones. So I run line 26, 27, and then 28. If I want to see the structure again, so it's going, this is what it's giving me. Now things have changed. It is still telling me that there are 474 observation of 9 variables, and it's a data frame. I have gender, which is a factor with 2 labels. Then the job category is a factor with 3 labels. And minority, it's a factor with 2 levels. So we are still just going to do some few things. So when I come to line 30, I want to create contingency table. And we know that a contingency table, it has got 2 variables, all right? So still, I use the command table, all right? So inside my table, I put the 2 variables I'm interested in, all right? The first one is gender. I go to, this one implies, go to the employee data set, $sign, it like you're saying that pick for me gender, that is what I'm interested in. And then comma, and then also pick for me the what? The job category. So in case I run line 31, what I'm seeing is that I've got females, then males, F and M, that's gender. And then with the job category, some are doing clerical jobs, others are doing custodial jobs, others are managers. So remember, we are saying that you can run some simple statistics just to give you a feel of what your data looks like. And we are seeing that the female, we've got 206 females that are doing the clerical job. In the custodial, we don't have any, and then we have 10 managers. When we come to the males, we have 157 doing the clerical job, 27 custodial, and then 74 are managers. I can run the same thing, just we are saying that how we calculate, how we get, so I can use that and then run line 32. This time I want a table considering job category and then the minority variable. And of course, I can read my results the same way as I did earlier. All right. And then after that, we say now we can as well from here, go ahead and run the chi-square test. Still the command is chi-square. And then inside, we put our 2 variables. You want the chi-square of what? I want the chi-square of gender. When you come to line 35, I want the chi-square of gender against the job and the job category. Is there any independency of the 2 or they are dependent? Okay. I can do the same with table 27. So I'm going to run line 35, and then you write for me the explanation in the chat. Okay, so here I run line 35. Now I want somebody to explain to me the results. I'm waiting in the chat. Can you type the answers there? Can you type the answers? Yeah, what does the results mean? Gabriel is saying that the variables are very dependent. Okay, Gabriel is saying that the p-value is less than 0.5, so it implies that they are dependent. Sami is saying that both are dependent. And then um, we accept the hypothesis, variables are independent. Steve, are you sure? Ah, Steve Odiambo, you need to check your conclusion again. Frank as well, you're saying there is no association between gender and job category. You need to check again. Why are you having that conclusion? Okay, the variables are very dependent. As P is less than 0.5, we reject the H naught. And the result mean a significance, statistical significance between gender and job category. Jeffers is saying that gender and yes, gender and minority are not are non-dependent. Yes, there I agree. But with the first one, gender is strongly associated with job category. Okay, that's great. I know there are many other answers that are coming in, but is large, gender, and job category are dependent. Wonderful. Okay, that's nice. So they have given us that conclusion. If we move on to the one of 37, still basing on the conclusion that we are having, in this particular case, we see that actually, if you run gender and minority, what we are seeing is that the chi-squared is really small, 2.3. Remember what I talked about, the divergency. And in this case, we're having our P as 0.12, which is greater than 0.05. So in that particular case, we have little or no evidence against the null. So in this particular case, we can say that the two variables are that there is independency within the two variables. They are not dependent. How about if you consider the job category? Let me check. Yeah, the job category, the conclusion is the same like the one of gender and and uh, and job category. Yes. All right. I think that marks the end for the chi-square test. Unless if there is a question, we can now change to part 2. Can we continue? Type 1. Okay. Yes, I've seen the different conclusions that you're putting in the chat, and they're right. Thank you. Okay. So for now, I'm going to stop sharing the R scripts, and then I share the slides. Okay. Okay, now let's move on to something also interesting about the general learner's model, and this is a logistic regression. It's also a common type of regression that is being used, especially for people doing surveys. Yeah, you can be able to go ahead and adopt it. But we need to first understand when they talk about logistic regression, what is it? What does it do? Um, are there some assumptions that we need to prove? Maybe I didn't get into those details, but it's also important that when you're looking at your data, you need to check that, okay, with the data that I have, does it suit a logistic regression model? In this case, we shall consider a binary one. Just some take homes that we need to understand, or understanding the basics, which are important for us to be able to interpret our data very well. All right. And then it becomes easy for us to know what exactly is happening when it comes to logistic regression. There's some common terms or concepts that we are going to see, or that we need to carry on within logistic regression. And these ones, we are going to have the odds, we have the odds ratio, the p-values, and then the confidence intervals. Why I'm saying that there are key terms that we need to put at the back of our mind, because at the end of the day, when we're reporting our data, these are the things that we need to put into our publication, all right? So where, for example, when you're drawing out your logistic regression table, what things are expected of you as a researcher, like what results are expected of you to be considered within your write-up. Okay, let's get started. So we need to understand what are odds, okay? Because most of the time when we talk about logistic regression, you can't rule out odds, all right? And this is just the probability that an event will occur, all right, divided by the probability that an event will not occur. There are two things involved. One occurs, the other one doesn't. So if the probability of an event occur, we denote it as pi. Remember, with probabilities, they sum to 1. Or if you have a success and then failure, okay, P plus Q is always equal to 1. So if the success in this particular event, the event occurring, is pi, then for it not to be occurring, it's going to be 1 minus pi. That is the failure. And so when we are looking at odds, so it's going to be pi over 1 minus pi. All right? And that is the formula we can carry on. So let's assume that the probability that an event will occur, it is 0.8. So for it not to occur, it's going to be 0.2. That is the 1 minus 0.8, and we come up with a 0.2. So that one gives us an odd of that particular event, whether we are looking at happening and not happening. Okay. And then also, when we are looking at logistic regression, we are in this presentation, we are basically going to be considering the binary logistic regression. I'm not limiting you to other types of regressions, but you can go ahead and and deepen your understanding. There is no harm with that. And remember, research is a process. You get one thing, then you keep wanting to do the other. All right, so the question is, when do we use a binary logistic regression? From the word bi, it implies two, okay? And in this particular case, for us to determine when it comes to logistic regression, most of the time we need to understand, how does our dependent variable look like? Call it a response, call it an outcome variable. Okay, so this one is always binary or you can call it a dummy variable. I think a colleague was talking about how to create dummies yesterday. All right. So it's supposed to be in a binary form. Okay, for example, yes or no. So that is what is expected of your dependent variable. So you can code it a 0 or 1. 0 could be here what we are having, did not vote, and then 1 did vote. All right? If that is my outcome variable. Another example we can consider for smoking, whereby Y is my dependent variable. All right. And so I can have still two possibilities, non-smoker, then smoker. Another example you can consider, it could be success of a medical treatment. Yeah, somebody went for treatment, but there are two possibilities that are involved. Either this person survives or this person dies. And there are many examples that you can consider, like I've listed. You can talk about predicting a disease, whether it will come true or not. Some of you that are within the financial inclusion, you can also look at the loan default, whether somebody defaulted or did not default. All right, etc. I mean, the examples are endless, but what is important that you need to keep at the back of your mind is that when considering a binary logistic regression, you have to first look at how does your dependent variable behave. If it is binary in nature, then now we want to move on and check how does other predictor variables influence this dependent variable. Okay. Like I mentioned, with the binary logistic regression model, we can still write it out. We are having, okay, before I put that, y, which is binary, yes, for all cases. I've explained that, but sometimes you can start including in predictors, or call them independent variables. You can start with a single predictor, implying that you're only considering one variable, all right? And so in this particular case, remember what we talked about, the pi, that is the success, proportion of success of any of this single predictor in this particular case. When you tend to check in different textbooks, or I mean, when you check on internet, how this the binary logistic regression model is written like in a logit form, we say it is the log of how the y is being written. It is the log of pi over 1 minus pi. All right, which is equal to, so the log odd, remember pi over 1 minus pi, these are odds. Okay, so the log odd in this case, which is we are looking at the probability of success, depending on whatever your dependent variable is, has a function of beta naught, which is our intercept, and then beta 1x. Here we've only included only one single predictor, that is the x. Since our pi is within probability of success, we can as well also go ahead and write it in probability form. And how do we do that? Is that we just need to make pi the subject, and so we can take exponential on both sides and then make pi the subject, and so it will come up like that. I'm just giving you a little hint of how it comes about, and then also we are going to move on and see how does it run in R. There are also scenarios whereby you've got some other variables that can influence you've got some other predictors that can influence the response variable. All right. The case whereby you have only a single predictor or a single independent variable, we refer to it as a simple binary logistic regression. But in case you've got multiple predictors, so in that particular case, we usually refer to it as a multiple binary logistic regression, implying that we increase the number of the predictors. Instead of having one, like we had for a single one, we can add as many as other predictors as we want. Remember, yesterday they discussed about model building. Still, within the many variables that you have, you might need to do, you go in for model building, and then you check among these many variables, which one will affect the log odds, which one will affect the probability of success of the different predictor variables. So still, if you consider the logit form, here what I did, this other side remained the same, my response variable, but what I only did is the addition of other variables, independent variables. The same thing with the probability form. We just need to take exponentials on both sides, such that we make this the subject. So then sometimes when you're writing out when you come to the data analysis section, the editor or somebody reviewing your work might be interested to see what is the formula of a regression that you are using. So that's why I'm putting some emphasis here. Okay. Most of the time also, when you want to look, I think Prof was discussing about different indicators whereby we saw that, okay, what happens maybe in case linear regression, simple and multiple doesn't work. And we saw some cases whereby you come up with a cubic form, implying that you might need to use different polynomials. But also, when it comes to a logit function, it is sigmoid in nature, whereby it runs from minus infinity to positive infinity. And in this particular case, the data is being seen as sigmoid, the way you see this red line. And it's also good to note that the logistic model assumes a linear relationship of the predictors and the log odds. Remember, this side is where I have the log odds, and then the linear relationship we are talking about, it is on the right-hand side. All right. Yeah, I've already talked about that. In case you want to get only, remember what these are the whole of this gives me the odds. So from the odds, I've already explained this, I think, in the previous slide. Okay. Another important concept that we need to put at the back of our mind, which is also important when we are looking at logistic regression, these are the odds ratios. Now that we know what an odd is, all right, probability of success over probability of failure, whatever event that you're looking at. So what is now new is that here with the log odds, we want to compare two groups, okay? And when we are comparing two groups, we look at their ratio. So the ratio of their odds gives us what we call the OR. Sometimes the odds ratio, it's denoted as OR. So if you're considering, you want to compare two groups, how their ratios look like. So with the OR, we usually have the odds for one group over the odds for the other group. All right, that is the odds ratio. All right, and also it is important to see that when it is greater than 1, we are going to find such scenarios. When it's greater than 1, most of the time we say the event is more likely to occur in group 1. Okay, when it is less than, then the event is less likely to occur in the first group. Of course, there are different interpretations on how people go ahead to interpret this result, but usually the conclusion is the same. Um, um, some of them might not want to use more likely, others might want to interpret them in forms of percentages, but the point is that understanding the concept behind what we are doing. So how do we get the odds ratio, which is very important? So from the log odds, if you saw that in case we exponentiate, all right, if we exponentiate the log odds after like running our analysis very well or getting the output in R, if we exponentiate the estimates, which are the log odds, then we come up with the odds ratio. That is a simpler way that we're going to use in R. Okay. We are going to take this simple example, which talks about the relationship between treatment and pain relief for migraines, or you can call it headache. And in this particular case, the two groups that we are having, we have treatment and then pain relief. Both are categorical in nature. Under treatment, we have the TMS, and then the other one is a placebo. So these are the treatments for migraine. And then with the response, we want to see the pain relief. Is there any relationship between treatment and this pain relief that they are giving? So basing on this, if this is my contingency table, looking at the response variable, those who said yes, that is a probability of success that the TMS, they are 39, and then those who said no, they are 61. So here we have two, the probability of success for that when we use TMS, we relieve the pain. All right. So now for us to go into odds, to get the odds for the TMS, it implies that we get the success over the failure. So implying that's going to be 39 over 61. The same applies to the placebo, whereby we shall have 22 over 78. So what we are seeing first is that we are getting the odds for each treatment. And then after getting the odds for each treatment, now we take the ratios of these odds, giving us the odds ratio. All right. So remember with group 1, which is the TMS, okay, we are having, so our odds ratio is going to be equal to, we're going to have the odds of this, of using the TMS for pain relief, and then the odds of the what? The placebo. So what we are saying that in this particular case, we are having the odds ratio we are having 2.27. So it implies that the odds of using TMS pain relief is 2.2 times the odds of using placebo for pain relief. Somebody can say like that. Or another one can say that the TMS when you can relieve pain 2.27 times than the placebo. Why I'm using time, we say that when it's greater than 1, so it's more likely. So that's why I'm saying that the TMS treatment is 2.27 times more likely to relieve pain than the placebo. These are when you read different articles, these are some of the ways on how these results are interpreted, in the sense that different disciplines can be able to understand how you are interpreting your results. Okay, let me first pause a little bit and I ask in the chat. Are we on the same page? We are still running into the theory before we get to the practicals. Okay, wonderful. Okay, I also welcome contributions in case maybe you have a different way on how the odds ratios are being interpreted. That will be great, all right? And then we expand on our understanding. Thank you. Okay, let's continue. So from that, now when we go to R, this is what we're likely to this is basing on the on the previous explanation. We are having to this result was coded into R, and I'm just going to show you the output. Then I explain it briefly. After explaining it briefly, then we shall move on to R and then use a data set, all right? And then in that part, I would expect you to give me the answers. All right, me, I'm doing the explanation here, but we use the same approach when we are explaining other result. We have the pain relief, which is a yes or no, and then we have the treatment. These are the two variables with the TMS. Remember, both of them are what? Categorical. So what we are seeing here, this is the output that we expect to see in R, okay? Each time you're running a logistic regression. So I'm going to just go it through very briefly, and then later we will continue to see how can we run it in R ourselves to support us understand more. Okay. Usually, when we're running a logistic regression, remember we said it belongs to a GLM, linear models, all right? So our command is GLM, all right? This is what we are going to write. I'm trying to, like, this is the object or the name of my logistic regression model. So what we have here first is that is our Y variable. In this particular case, it's pain relief, which is either yes or no. But in this case, if we continue to R, we just need to put the name of our response variable, and then we indicate that data equal to this. But it's just an explanation. And then this group, this is the group of treatment. This is our predictor. It is a simple linear regression. So in this particular case, remember there are two groups. We have within the group of treatment, we consider the TMS for migraine and then the placebo. But what is our family? Our family is a binomial because of the binary nature of the response variable. And we are saying that another argument that we have, it is data, which is the TMS data. So this particular line, it shows the model formula and the data used in the analysis. Our model formula, which is the GLM, and then the different data that we are considering inside, we have the variables, we have the family, which is a binomial, and then we have the data, which is the TMS. All right? Sometimes, then from there, we can run the summary, like the way how my colleagues have been using these commands. Summary, then in the summary, we put the what? We put the name of our model, which is the L mod. So next, what we are seeing the coefficients, all right? With the coefficients, we have the intercept and we have the group TMS. But let me first explain with the estimate. This one is these are the estimated coefficients for the predictor. And in this particular case, for example, we have our intercept, which is a minus. It might not really give a lot of meaning, but with this other one, the group team, we're having our estimate as 0.8184. And so this one represents the log odds of the response, the log odds of the response between TMS and the placebo. We also have the standard error. In this particular case, what usually the standard error does, it measures the average amount that these estimated coefficients vary from the actual values of the parameter. I'm just revising or with you what my colleagues were giving you. And we have what we call the Z value. With the Z value, this is the test statistics for the world test. And it's usually gotten by getting the estimated coefficient we divide by the standard error. And what it does, most of the time, it tells us how many, it measures how many standard deviations the estimated coefficients are far away from zero. And then when we come to the probability value, all right, the probability value is also associated with the Z value, but most of the time, like how the training has been going is that we look at it to see if it is less or if it is less than 0.5 or greater than 0.5, or depending on the statistical codes that are being presented. And those are our results. So when you come down here, we have what we call the null divergency. With the null divergency, it represents the divergence of the model with only an intercept, whereas the residual, it represents the divergence of the model when other predictors are added. And then with the AIC, that is the information archive criteria, as it was explained yesterday, it measures the quality of the model. All right, and we say that maybe in case you're comparing different models, the one with the lower AIC, it usually gives us the best fit for our model. Okay. So again, in this particular case, like I mentioned, that usually the quick interpretation, it is always good to exponentiate the estimated coefficients. If you exponentiate the estimated coefficient, then you come up with what we call the odds ratio, okay, for these two groups. And still, our estimated coefficient of 0.818, if you exponentiate it, we go back to the result that we got earlier on the previous slide, which is 2.27. And so we still, if in this case we have group TMS, that is the treatment, then the placebo is now the reference category. And still we can conclude and say, using placebo as a treatment relief is 2.27 times more likely to reveal pain than the placebo. Basically, that's what we are seeing here. Okay, I've put a simple exercise for some of you in case you're interested. You can run it in R. Then we'll see. Maybe, I don't know if I have it still in R, we can run it together. But what we are having is that the logistic regression example, we have a data frame, which a data set, which I refer to as DF. Within a data frame, I created only two variables, all right? The outcome, which is a yes or no, 1 and 0. Then we have the age. And we mentioned that now that our outcome is a yes or no, so we just need to call our model, in this particular case using the GLM, yeah? Then you put the output, the relation between the output, the response variable, which is the outcome, and then age. In this particular case, what maybe that I need to know that age is continuous. I put another argument of data, and then I also put my family, that's binomial. And then I can go ahead and put the summary, okay, of that particular model. If you want to do prediction of probabilities, I can go ahead and use this command. I put my model, this one here, and then the argument type, I indicate the response. Okay, we can try out that exercise. So I think that theory is enough for us to understand. So what we are going to do, we are going to move on to R and then see in case somebody wants to run a binary logistic regression, having tested that is the one that is suitable for his or her data, how can it be done in R? Let me check in the chat. Are we on the same page? Type 1. Okay. Okay, great. Okay, now let's go back to our R script. All right, we are still using the same script. So I'm going to stop sharing this. Okay, then okay, we are still using the contingency chi-square.r script. And you see that there are different sections in there. And I've put comments that are now where we are going here. We're going to look at logistic regression. So I would encourage you, I don't know whether you've installed these packages that we need. We need the package cult, because it supports us to run the inbuilt functions of the GLM of a binomial, the family binomial, since it's by in nature distribution. And then also we need the library tidyverse. So I'm not so sure if you have them. If you do, kindly run them. Okay. Now I wanted us to so it is telling me that load required package lattice, but what is important are these two, but it's okay. Library. Oh, gosh. Okay. Okay. We are going to use, in this particular case, we are going to use the data set, which I named mydata.csv. Still, when you check in the folder that we uploaded and in the material, you will see the mydata.csv. Apart from that, there is also a description of how this data looks like. All right. So I'm going to first stop sharing just briefly. Then we see the description of the data. But still, this Word document still among the things that we uploaded. Okay, here what we are having, for us to be able to analyze our data very well, it is always important that you understand the nature of your data set. That has been a song from day one up to now. Because if you don't understand it, then at the end of the day, you might use a wrong statistical test. So with this one, with this my data set, it's looking that a researcher is interested in how variables like the GRE, that is the Graduate Record Examination Score, the GPA, the graduate point, which is the graduate point average, and prestige of the prestige of the undergraduate institution affect admission into the graduate school. In this particular case, what we are having is that the response variable, it's binary, implying that either one is admitted, so we want to see how do these other variables affect one's admission into a graduate school. So there are two possibilities. Either one is admitted or is not admitted. That is our binary variable, which is the response. Both the GRE, the Graduate Record Examination Score, and the grade point average are continuous in nature. But when we look at the rank, okay, the rank, they're saying that what does it imply? The prestige of the undergraduate institutions is categorical and it ranks from 1 through 4. 1, that is the highest prestige, then we have 2, 3, and then 4 is the lowest prestige. So maybe you can say rank 2, maybe it's not the highest. We could say it is good. Then a 3, we can say it is fair. I mean, you can judge, but what we are being given are ranks, and so the ranks of these institutions, it is categorical, all right? And the admit, okay, this is the response variable, which I've already mentioned, that either somebody is admitted or not. So do these other variables affect one's admission to graduate school? Now back to R. Okay, back to R. Let's import our data set, which is called my data. So I'm going to run up to line 51. So, I mean, I already have the same working directory. What I need is I'm calling my data set. I'm giving it the object name of graduate. So I run that and I can see it in my environment. We have 400 observations of 4 variables. Well, I can call the names in case I want to remind myself. I know they're already 4. Admit GRE, GPA, and then rank. All right. Where you're seeing the greens, those are just comments that I was just trying to like, okay, in case I get back to use the same script to support me easily remember what each variable is. Okay. Let me first ask, have you been able to call the my data CSV in R? Okay, great. Then another question, did you succeed in loading packages tidyverse and cult type 2? Now let's type 2 if you succeeded. Okay. Wonderful. In case there's somebody who has not succeeded to load those packages, you can type in the Q&A and then they'll give you help. What you can do, you can copy the error that you're getting and then you paste it in the Q&A. There it becomes very easy to be guided. We need these packages because if you don't install them, then we are going to come up with errors because the functions that you want to use are within these packages. Okay, let's continue. I think now we know what the head does, the head command. I hope I'm right. Okay, we said with the head, it gives, by default, it gives you the first 6 or 5 rows, just to check on how your data looks like. Just here we are seeing our 4 variables admit. Yes, we can confirm that it's binary 0 or 1. We have the GRE, we have the GPA, and then we have the rank. Okay, remember with the rank, it's the admit and then the rank are categorical, the GRE and then the GPA are continuous. Okay. Sometimes it's good to run the structure of your data set to confirm that you know what I'm doing is okay. These are some of the commands that you can test all the time to be sure. So what we are seeing with the structure of the data set, it is telling us that admit is an int, which is not true. It's an integer. At the same time, it's also saying that rank is an integer, but this is not true. As far as the data that we collected is concerned, or the description of the data set that we have, we are told that admit and rank are categorical. So we go ahead and use as a factor to convert admit and rank. That is line 6 on my end. It's line 63 and then 64. So I come, I run that, then I check again. I think now everything has changed. That admit is a factor with 2 labels, and then rank is a factor with 4 labels. We can do some summary statistics in case we are interested. That is line 68. Hope I'm not very fast and I'm not confusing anyone. So what we are seeing here is that those that are not admitted are 273 and only 127 are admitted. The GRE is a summary, it gives us a summary statistics of from minimum to maximum, same applies to GPA. And then with the rank, which looks at the prestige of the university, we have we have 61 into 151. When you go to 4, it is 67. Okay, I've already talked about creating a contingency table using the table command. That is line 72. Okay, so here we're having 2 variables, admit and then rank. So if we can still briefly talk about this, 0 not admitted, those that were not admitted in rank 1, there were 28, in rank 4 there were 55. Those that were admitted were 33 to rank 1 and then 12 in 4. I'm gonna leave that. Then 76, it gives you the same results as the above. So I'm going to scroll and then come now on line 83. Because I think with the previous commands, we can now understand them. Gitzel is asking, what is the threshold for admission and not admission, please? In this particular case, we do, the being admitted is just our response, okay? Or you can call it the outcome variable. So we want to see how other variables, the predictor variables, influence somebody either being admitted or not admitted to a graduate school. That is the information we have within our data. And then somebody says, can you repeat line 50? What is in line 50? Oh, no. With line 50, we're just importing our data set using the read.csv command. That's what it does. And I labeled my data set as graduate. I hope that is clear. Ensure that you import the mydata.csv. Okay. Okay, now let's move on and run the first part. Okay, I've seen it, great. So we're going to first run a simple logistic regression. With a simple one, we are only going to consider one, predictor, okay? Remember what I'm now calling my formula. I'm calling it logit1. This is just an object name. If you're not interested in that, you can change it to something different. All right. And then I'm using the GLM. The GLM is my command that I'm using. All right. And so this is my response variable, admit, either somebody's admitted or not. This is the GPA, which is continuous. The data I'm considering, like the way I was showing you the other output. So now we are writing it in R. The data is equal to graduate, and then the family is binomial. Okay, so we run this line. When you run that line, for you to see the summary of the result of the logit1 model, you run the summary command. When you run the summary command, this is what we are coming up with. Okay, remember we have this, like the way this is our formula. We have the intercepts, okay. We have the significant codes, like whatever that, then we have the null divergency, which I explained. It's the same explanation that I talked about earlier. We have the number of phishing square iteration. That one just tells us how many iterations that the model went through before it converged. Okay, so in this particular case, we have a 1.051. Okay, and I mentioned that in this particular case, when you want to explain these variables, especially when you're putting them in your publication, it is always good that you consider explaining the exponents, all right? How do we get the exponents? We exponentiate the estimated value. In this particular case, we exponentiate the 1.0, the 1.05. So how do we do that? The rest of the thing remains the way as I explained. Remember, in this particular case, so what maybe somebody might want to ask, how, when you're looking at that, the 1.05 just represents the log odds, okay? of the log odds of our outcome, which outcome is the admission for a unit increase in the GPA, because it is continuous in nature. But now let's go back and see, how about in case we can get the confidence interval. Still, the command is conf, all right, of your model. Then how do we get the exponentiated value? We use this one is the CEOF, this one is conf, coefficient. We can also come up with well, I'm going to run, then I come and I'll explain now from line 98. I can run my confidence interval for that. Okay. It gives me what I'm seeing in the console. After that, I can pick the coefficient only. That is the beta 1 for the GPA and the intercept. So this is what I already have with what we saw in our model. So in case we want to get the odds ratio only, so what we do, we use the exponent, EXP, and then inside we put the coefficient. Yeah, so when I run that, it is able to give me that the exponent for the GPA, it is 2.86. Okay, so now what I'm going to do, I'm going to bind the odds ratio and the confidence interval together, and that is the line 98. When I do that, this when you look down here, these are the final results that I have. Okay, now I want to ask anyone from among our participants who can explain this particular result. Remember, we are only using the GPA, all right? And we are told that the OR, we can consider up to 2 decimal point, it is 2.86. How would you explain that result? Let me check in the chat. You can, oh, somebody had already given me the 2.86 as the odd ratio. That is great. What is GPA? If you check in the description of the data set, the GPA is the grade point average. Okay, thank you. I think also your colleagues are trying to answer. Okay, now what I want to see is that who can explain to me? I've gotten my OR as 2.86. Gent is saying that it means the GPA influences 2.86 times the admission. All right, thank you. Can I get more people? Please type in the chat. It means okay, Gabriel is saying the GPA is 2.86 and it increases the times likely admitted by that, all right? The probability of using the GPA for admission criteria is 2.86. Great. Okay. With OR of 2.86 means GPA can influence the admission by 2.86 times. Yes. Okay. I'm reading out all your comments are really good. Then a unit increase in GPA from Slivia is likely to increase the likelihood of somebody to be admitted by 2.86. I think we've had all the different submissions from our colleagues, and I concur with them. So somebody can conclude that since ROR is greater than 1, so for any 1 point increase in the GPA, like I mentioned, it's about understanding how you give an interpretation. All right, a student is 2.86 times likely to be admitted into a graduate school. That could be the explanation I can give. Or somebody can say that for a 1 point increase in the GPA, a student is about 2.8, or we can say 3 times more likely to be admitted into a graduate school, which is the same as what you've explained. So I concur with your explanation. Thank you so much. That was for the case of the continuous, and we're only using one continuous variable. Now, let's move on to the cases where we have a categorical variable. And still we're first considering only one variable, which is categorical. All right. And then we are going to consider multiple, where we are adding all our variables. Why I broke them down, I wanted us to understand, okay, in case you're considering a continuous, how do you do the interpretation? In case you're considering a categorical, how do you do the interpretation? But at the end of the day, as we move on to the multiple one, it is just like seeing the contribution of each predictor variable, keeping other predictor variables constant. But let's first do the one of categorical. And then also, I'll ask the same thing that I want to hear from you. What would be your explanation on this? The procedures are the same. What is changing is now we are using the rank. Remember, rank is categorical from rank 1 to rank 4. I'm not changing anything. I'm only changing just here with like I put in the notes, we are considering with categorical, and then the last part is going to be multiple, and we end with logistic regression. Okay, so let's run line 103. When you run line 03, it's the same thing. I get my summary. I'm going to skip that because I want to say that one gives me the confidence interval, it gives me the coefficients only. I'm interested in the exponentiated values, which gives me the odds ratio. And then I can bind them together. All right. When I run this, okay, when I run the last line, the 119, I want to run line 1. Yes. So when you come down here, what we are seeing is that we have the odds ratio with their respective confidence intervals. All right. We are seeing that rank 1 is missing, so it is acting as our reference category. We are comparing. Okay, what is the we are considering rank 1 as a reference category, as we are looking at the log odds of 1 being admitted basing on the different ranks. Okay, I'm going to ask again. Basing on the results that we have, how do you explain, even if you just give me for only one? Yes, we know with the intercept, the other rank is embedded in there. It acts as a baseline. So now, looking at these results, we can still take up to 2. Let's take for rank 2, because the moment we understand for the rank 2, then the other explanation is the what? The other explanation is the same. Let me check in the chat, please. Yes, Livia, great. The best category is rank 1. That is wonderful. Now, how do you explain the odds ratio of 0.47? type in the chat and then I'll read out. The moment that one is clear, then it will be the same explanation for rank 3 and rank 4, since all of them are what? Are less than 1. All right? But I'll be glad to first see how would you explain that? You need to qualify for rank 1 to be more likely to be admitted. Rank 2, 3, and 4 are more likely to be rejected. That is Amuli. Thank you so much. Okay, that is his submission. Gabriela is saying that rank 2 is less likely to influence admission into rank 1 by 0.47 times. Maybe that is true. As you're typing your submission, you can also think through and say that really does this result that I get really makes sense. You can also understand it, like how Gabriela said that within rank you're less likely to influence the admission into rank 1 by 0.74 times. So after looking at our data, we need to also put our intuition, we need to put our own reasoning. Why is it like that? Remember, rank 1 is the highest prestige institution, all right? So why is it that my results that I'm having, that the chances of being admitted from rank 2, they are less by 0.47 times? Great. Shayla is saying that since 0.47 is less than 1, then the rank option wouldn't be used to influence admission. Okay, wonderful. So if we are to look at that, just to sum up with the categorical, we can say that how I would explain it, that students from rank 2 schools or graduate schools are less likely to be admitted to rank 1. And, that is what most of the submissions are having. There is 0.47 chance of a student of rank 2 to be admitted to rank 1. Thank you so much. I think we've gotten that bit as well. So now the last one, which is the GLM. So, sorry, the last one is a multiple logistic regression model. Like the way we explained the simple, it is the same thing, only that in this particular case, we are putting all our variables together. That is the only difference. But the model, how to write the model, all the things are what? All the commands are the same. Remember, with R, you can reproduce these codes depending on the project that you're working on. So, for example, if you're working maybe on experimental designs, then you can use the codes for Dr. Thomas. You reproduce them to your what? To your research, but you just need to adjust a few things, understanding what each command does. If you're running, for example, with the regression analysis and then the correlation, you can reproduce the different codes by Professor Susan and then also relate them to what? To the project that you're working on. What is important? Understand what each code does, understand the explanation of each, and then the other bits can be reproduced in the different projects. Okay, I ran that. I'm just going to run this because I know now we know what we are doing. Then I get the exported, and now this is what I have. I've been able to come up with the OR, the odds ratio, for all my other variables that I've included into the model, as well as their confidence interval. Sometimes we can also, it is important to compute the p-values, and it's also doable. We can come up with the p-values as well, and So when you're reporting, most of the time, you have to report your R, you report the confidence intervals, you can also report your p-values. Okay, let me check in the chat if there is okay. So basing from what I'm seeing, can you type 1 if all is well in the chat? Okay. All right. Okay. If there is a burning question, you can type it in the Q&A. My colleagues are on standby to support. So now let me ask another question before we move on to the last bit. Do we need a break of 10 or 5 minutes? Or I just continue? Okay. Majority are saying that I continue. Others are saying break, please. So, break. Okay, what we are going to do, let's only take a break of 5 minutes instead of 10. All right. So we start at 4 um at 4:29. Only 5 minutes. Let's start at only 5 minutes. The moment it clocks 4:29, I resume again. Now we are going to move on to the last bit, which is also, it's not really a lot, just a brief about the Poisson regression. I'm going to just talk about it briefly, and then we run the R analysis. I'm hoping it won't take a lot of time. We also have the evaluation form that we want you to fill. Maybe during this break, you can do that. Dr. Thomas and Prof, what do you think? Are you there?
Yes.
Yes, we are.
Can we share the evaluation link in this time? The
Yes,
break?
you can share.
Okay.
I hope okay. Yeah, share.
You have one?
That's why I was wondering because I forgot to
You just copy it in the chat. You've
the
seen
the
it?
one I shared earlier is the one for the Q&A for the
Yes,
experimental design.
but this one is the
Okay, that's fine.
evaluation for our
Okay,
training.
that is good. Yeah, I think this is the right time for them to do.
I've put in the inbox. You can check.
Dr. Helen. Helen,
Yes, please.
do you have the questionnaire
Which questionnaire?
for this 5 days?
What do you mean?
Evaluation form.
I
It's
think
what
she
I've
shared.
I inboxed you. You check in
Hey,
I sent
the
one
email.
direct to you.
Okay.
It's in the Google form. It will be easy for us to capture the responses. You seen it?
Okay. Let me go there.
I've also pasted it again to everyone. You can also pick it from there.
In the Google, in your folder.
No, in the chat.
Oh, you formulated that. I thought it was under these notes. It's
No,
a
no.
new link.
Yes.
Okay, okay,
It's a link that we are sharing.
okay.
Yeah, Google Form link. Okay, you've seen it?
Let me check in the chat.
Mm,
Yeah, I've seen Google form.
yes.
Okay,
It's the evaluation one for
okay,
for this current training.
okay, okay, okay.
Mm,
Let me just also keep posting it.
okay, great. Let's continue. I'm hoping to use a fewer time, and then we talk about
Then you
some
present the TDA.
the what?
You present the consultancy firm.
I thought you are the one presenting. I presented.
Present! You present!
Okay, let me quickly first go through the
You want me to present?
I have
Are
no
you tired?
problem. You're tired. Okay.
No. If you're tired, then I present.
Mhm.
Oh, yeah. You should finish before 5 because today's jam day.
Yeah.
Mm?
Um.
For you at home, yeah, I'm at forum. You people shan't do forum here alone. Even Thomas said would come and take me out. He's there just hiding himself.
No, I had to attend I had to attend a PhD defense in the morning, so I couldn't make it from home to campus on time, so I decided to come to Kabanyolo so that I
Or you
can
are
do it
dodging
online.
to buy knickers.
We'll do that. Maybe Selma and Atur will take you.
I don't know.
And at least Ellen promised me KFC.
Really?
Thomas, are you serious?
Hey, you've forgotten.
I'll take both of you.
Okay,
That would
that
be
is
good.
good.
When is that? I need to remind you.
Okay.
Next week.
Next week,
Mm.
I'll let you know. All
Okay.
Okay.
right. Participants, I hope you're back. Let's briefly talk about Poisson regression, and then if you get the basics, you can build from there. Um, when we talk
Helen, do
about,
they have these notes?
sorry?
They have the notes in the Google link?
Yes, I uploaded
Okay.
everything. They do.
Okay.
Mm.
Okay.
Um, We know that with Poisson regression, this kind of regression is used when you want to model the number of times an event occurs in a fixed interval or in a given space. Unlike with the logistic regression, where we considered a binary response, in this particular case, our response is the data is count data from 0, 1, 1, 2, 3, and so on. One of the main assumptions that you have to consider when you're running a Poisson regression, the mean should always be equal to the variance. And the simpler way you can write this model, it is the log lambda, which is equal to beta naught plus beta 1 x, if I consider a simple one, considering only one dependent variable. And with the lambda, when you're looking at the different distribution, is usually the expected number of occurrence. All right, some people call it the average occurrence rate, depending on how you want to interpret it. And it has got many applications. For example, since we are saying that it's count data, we are having like the number of accidents that can happen within a day, number of visits per hour in a hospital. You can talk about insurance claims per month. You can also talk about the number of emails that you receive maybe before lunch. All these are counts. These are responses that you can consider. Some other assumptions that you can talk about is that we know that for Poisson distribution, yes, the average rate, my lambda, is constant, all right? And events occur independently. So just briefly about the probability mass function, how it looks like. We know that a Poisson is a discrete kind of probability distribution. So the probability that my response variable will give me maybe a 1 or a 2. This is a small x. It's usually denoted as this, all right? And then the outcome, x starts from 0, 1, 2. You can label the x with any variable that you want. Maybe what is the probability that the number of claims per month will be 5. Okay, that is my small x, that it will be 5, etc. I've already talked about the lambda, which is the expected number of events. All right, we need to put that into consideration. And then also the mean and the variance have to be the same. And you can easily check those ones into R. I'd put a practical that we can consider. Or let's take our response as the number of doctors' visits. All right, and then this one is the probability mass function, the R poise. So we can have the random, 100 of them, the number of visits, and then we consider our expected as 2. And then we also have the age, and then we can run also, when you're running a Poisson model, you use the GLM, okay? Command your response, in this particular case, the number of visits as a function of age, and then the family is Poisson. Then after that, you go ahead and run a summary, you use a summary command to give you the different output of your model. On this other side, we are having a data frame, still an example. We have this example within the R script, so I'm going to give more explanation from there. We have the visits that somebody makes, the accounts, 2 visits, 0, 3, 4, etc. It's an account, an outcome. And then our other variables we have is age, then gender. Then fitting a Poisson, it's the same. Here we are fitting both variables. We want to see the contribution of age and gender as per the number of visits. And then our data, which is I have there, and then the family is Poisson. And then we run a summary. But also still within the Poisson regression, we can be in position to compute the odds ratio. But what is different here is how do you explain your output in R? It's the most important. In summary, looking at the compulsion and the key assumption, especially of the three tests that we've looked at today, with a chi-square, we say you have two categorical variables, so categorical versus categorical. With logistic regression, what you have to know, these are binary outcomes, and then with Poisson, they are counts. And for a chi-square, the key assumptions are we have independent observations, and then usually the expected counts are large. With the logistic, the key assumption is a binary outcome and independent observations. When we look at Poisson, since it's a count data, the mean is approximated to be equal to the variance to avoid to check for over dispersion. So on this particular slide, I'm going to explain something briefly, then we can go and run an R script, and that will be the end. And also, maybe just remind you that a Poisson is log linear in nature, so we cannot have a perfect linear relationship. For it, it's log linear. Assuming I have just my log of lambda, okay, when this one is equal to, I have beta naught. This explanation will be enough for us to capture everything within the R. I'm going to consider x1, then I add beta 2, then I put x2. All right, I can rewrite the same. Remember, we are looking at the log expected count. I can rewrite this in a more understandable way. Maybe if I'm to consider the variables. So here I can say this side I've got the expected visits. Let me write it as V, but these are the log of the expected visits. All right, that is my lambda. And then I can say this one is equal to beta naught, and then plus this, that's my intercept. I write beta 1, and then my x1, I can consider, let me call it age from what we have the other side. Okay, if this is my age, and then I add my beta 2, and then age is continuous. This one is, let me put gender. Okay, gender with the F and M. All right, this is what we have. So when we are explaining in this particular case, you might ask yourself, this is my Poisson regression model, where I've got the log expected number of visits. Remember, we are looking at our response is a count. Okay, so how would you interpret beta naught in this particular case? Beta naught would be the log expected number of visits when age and gender is equal to 0. All right, and then when we come to age, we want to see how do the number of visitors vary with the unit increase in age. Okay, that is what we want to see. How do the number of visits vary with the unit increase in age? Okay, in this particular case, keeping gender constant. And then when we come to the gender, we want to understand also it's the same thing, that how do the number of visits vary between males and females? That is the gender part of it. Okay, but also like I mentioned, you can also go ahead and we can come up with we can exponentiate the estimated parameters, and when we exponentiate them, we come up with the odds ratio. So when we exponentiate the beta naught, remember this is our intercept is going to give us the expected number of visits, because if you put an E there and E there, then we're only going to remain with the expected number of visits. And then if you exponentiate beta 1, this is the estimate that corresponds to age. Let's just take an example. Maybe, for example, we come up with the odds ratio as 1.24. I'm just giving a literal example. That one would imply is that any additional increase in age will increase the expected number of visits by 1.24, holding gender constant. Or you can say any additional increase in age is expected to increase the number of visits by 24%, depending on how you want to look at it. When we come to gender, let's just assume that our exponentiated beta 2 is 0.99. I'm just giving a field such that we go to R and run the result. Remember, with the gender, we have both males and females. If we consider female to be the reference category, like the way we did it for the logistic regression, then we need to ask us, then in that particular case, it will be that males are 0.99 times less likely to make visits than their female counterparts in the same age. In other words, the males, it is only males are 1% less 1% less likely to make visits compared to their male counterparts. So, like we mentioned again, all this goes back to your data sets and what exactly, what objective are you trying to achieve? Because in this case, we are modeling the relationship between the expected number of visits in relation to age and gender. You can look at them separately, or you can, with a simple Poisson regression, considering only age, or you can consider only gender, or you can combine all of them. But what is important here to notice that what we are modeling the expected, the log expected outcome, okay? Which outcome is the outcome is our response. It's a count that we are having in relation to other variables. Sorry. Okay. Now let's move on to our practicals briefly, and then the rest you build from there. Okay, when I go now to my R script, it is the same script I'm using, but I gave in different sections. All right. This is what I was explaining. Here I created an example of a data set, all right, which I called data. And in here, I've got 3 variables: the visits, which is my response. It's a count. I have 203 etc. I've got age, then I've got gender. So I can run the whole of that, okay? And then I create my data. So if I want to see how my data looks like, I've got there are only 10 observations, all right? And I have visits, number of visits, I have age, I've got gender. Like how I was explaining earlier, when you come now to fit the Poisson regression, we want to know, how does age affect the number of visitors? this is what we are having here. How does age affect the number of visitors? We still use the GLM. If I call it, I assign an object model 1, we still use the GLM, and then you start with your count variable, which is visits, as a function of age. All right. Now, the family, we put Poisson, and then another argument you need to add is the data, because as it runs, it has to recall your data. So what I do, I run this, I run that, I run the summary, since I want to explain in terms of the exponentiated or the odds ratio. I exponentiate the coefficients. So in this particular case, what I'm having here is that the exponentiated value is 1.04. Okay, so maybe how can somebody explain that? We can say that I remember in this particular case, age is what? Age is continuous. Since it is we can say 1.05. So with an additional increase in age, is associated, you can say by 1.05 times number of visits. Is associated with 1.045 times number of visits. In case there are some other variables, you can say holding gender or whatever constant. And we can do, then later, we can run when you're having both. Then we get the summary, and then we also get the what? Get the coefficients. But like I mentioned, everything remains the what? The explanation remains the same. Here we are modeling the expected number of visits as a function of age and gender. When we come down here, what we are seeing is that now this time around, like I explained with the categorical variables, in this case with the gender, we have M, and then female is our reference what? Female is our reference category. So and we are having it as 1.13. So here what we can say that males, the expected number of visit by males is 1.13 times more those of females in the same age category. Okay, I'm gonna stop there. Then the rest of other codes the same. It's just that I added from the data set. Over to you, Prof. Thank you.
Dr. Helen, thank you very much. Participants, thank you very much, forum. We have a short presentation about our consultancy firm, and I want to take a few minutes to present it. We have a consultancy firm called Tafit Data Consultants, and our vision is to be the leading provider of consultancies in research design, data analysis, and statistical modeling in Africa and beyond. Our mission is to ensure that research on the continent of Africa are well planned, effectively executed, the data thoroughly analyzed. We are committed to promoting the proper use of statistics in research in both natural and social sciences. We have a goal, which is to establish ourselves as the premier consultancy in research design, data analysis, statistical modeling in Africa by consistently delivering high quality, impactful solutions that enhance the efficiency of natural and social sciences research while fostering collaborative partnerships, and innovations. Our approach, we adopt a personalized approach, working closely with you throughout your research, from planning to the final presentation of results. We leverage over 20 years of experience in in-depth knowledge in statistics, quantitative genetics, bioinformatics, and research methods. We ensure the most appropriate research designs, data analysis, and modeling. We also assist you in formulating suitable research objectives, questions, and hypotheses, as well as determining the best strategies for data collection, analysis, and presentation of results. For postgraduate students, we offer excellent learning opportunities through guided data analysis, encouraging students to conduct their own analysis under the guidance of our experts. Additionally, we provide data analysis clinics where students can bring their data and benefit from a supportive environment to analyze it with the help of our specialists. Our consultants assures you that our well-trained and experienced team will help you to maximize the potential of your data. We are committed to letting your data speak nothing but the truth. By partnering with us, you can focus on what you do best without the burden of finding or hiring a full-time statistician. Our services, we can offer a range of short-term consultants to long-term collaboration. We can design studies, experimental and surveys. We can do data analysis and statistical modeling. We can establish and manage databases. We can provide advice on statistical software for use, and approving the statistical aspects of your research, proposals, and technical reports. We can prepare and revise scientific articles and reports for publication. We can perform research on behalf of clients. We can train enumerators, interviewers for data collection. This involves training of researchers or postgraduate students through short courses, tailor-made courses, designing data collection tools, e.g. questionnaires. Our target clients are university departments, research institutions, public and private companies and NGOs, academic staff, postgraduate students from various universities, also individual researchers. Our team have conducted over 15 national, regional, and international training to different institutions, including Ruforum from 2004 to date, Mackay University Regional Center for Crop Improvement, Center of Excellence in Agri-Food Systems and Nutrition, Uganda National Agriculture Research Organization, International Institute of Tropical Agriculture, International Atomic Energy Agency, among others. We offer the following short courses: Introduction to R Programming Language, Exploratory Data Analysis using R, Introduction to Statistical Modeling, Advanced Statistical Modeling, Introduction to Experimental Designs and Analysis, Advanced Experimental Design and Analysis, Research Methods, Multivariate Analysis, Categorical Data Analysis, Genome with Wide Association Mapping, and QTL Analysis, Qualitative Data Analysis, Sample Survey Methodology. And the consultants, we have Dr. Helen Namaweje, Dr. Thomas Lapak Odong, and Susan Tumwebaze. We have 20 years of experience in in-depth statistics, quantitative genetics, bioinformatics, and research methods. Thank you very much for paying attention. So in case you have specific problems, you can use, let me put back, we don't have our, let me see whether we have an address on the beginning page.
I've been putting the email.
Okay.
Yeah, I'm going to put the email in the chat.
Okay.
But the brochure that we provided us the contacts.
Okay, the procure in the Google Drive has the contacts, our contacts, WhatsApp contacts, and email. In case you have an individual need for in-depth training, you can always contact us and we'll discuss the modalities. I hand over to Dr. Thomas Odong in case you have anything else to say.
Just to say thank you very much to the participants and RUForum for giving us this opportunity. I talked about the Q&A session that we are planning to all together with RUForum on experimental design. I think we need to share a link, or we're going to share a link where you can put in your questions so that when we get the number of questions and we agree on the date, it will be announced and you'll get informed. So let me try to get the link and try to share here and now before we can go anywhere. So you can carry the link, go and try to see picked. You can take your time, just get the link, and then you can fill that anytime when you're ready. So I'm going to put the link here, but we're also going to, sorry, I put in the wrong thing. Yeah, thank you. I think back to RUForum team.
Very much. Thank you very much for taking us through this session, our dear facilitators. We really want to give you a round of applause for being very knowledgeable and providing us with a lot of knowledge, very practical. We really do appreciate your effort and your patience in this. To the participants, thank you very much for being with us. As usual, we are grateful to have you as part of our mission for capacity building in agriculture and other related sciences. So this is an indication or a submission for our capacity building to our universities across Africa. And we thank you very much for always attending and participating so that we meet on this goal and mission. We are going to send you with the certificates as promised, only for those who have attended all the five days from Monday to Friday. Your certificates will be provided in due course. Thank you very much and have a good evening and a blessed weekend. Bye-bye.
Bye. Thank you.
Thank
Bye-bye.
you. Bye.